everyone, my name is Xuan. I'm going to present our work Interstellar using Halide scheduling language to analyze DNN accelerators. This is a joint work with Mingyu, Qiaoyi, Jeff, Jing, Ankita, Steven, Kaidi, Heonjae, Priyanka, Christos, and Mark Horowitz. This work is done at Stanford VLSI group. Deep neural networks has been widely used in many different scenarios, such as autonomous driving car, face unlock, etc. For all those different scenarios, both performance and energy consumption are a big concern. That's why there is a lot of efforts for designing efficient DNN accelerators from both industry and academic sides. From the industry side, Google TPU targeting at high performance, low latency builds a large matrix multiplication unit. Huawei Kirin NPU target at mobile platform use DNN architecture. Iris team from the academic side build an ASIC chip, use the systolic array to optimize all kinds of data reuse. On the IPJ side, Zhang Chen and many other teams explored different mappings of deep neural network to fully utilize memory bandwidth and on-chip resource utilization. Let's briefly go through the computation of DNNs. Given a set of input feature maps, we can call them IF maps, which can be think of as different image channels. We also have a set of filters. In this example, we have two filters. Each filter has the same number of channels as input. Then we can perform a 2D convolution between each input image channel and the corresponding filter channel. After accumulating the results for all the channels, we get one output image channel. We call it one OF map. Mapping IF map to multiple filters, we can generate multiple OF maps. One common method to improve energy and performance is use batching. Instead of feeding one image at a time, we feed multiple of them. So now we have notations for all the dimensions of DNN computations. Nx, Ny for IF map width and height, Nc for the channels, Nk for the number of filters, and Nb for the batch. We realized the computation of DNN can be nicely described as 7 nested loops. From outermost to the innermost loops are the batch dimension, IF map, OF map dimension, feature map height, feature map width, and filter height, filter width dimensions. From this loop nest, we can see there is a large amount of data involved in this computation. Fortunately, there is also a large amount of parallelism we can leverage to improve the locality. And there are many ways we can schedule this computation to improve the locality. Therefore, the high dimensionality of scheduling leads to a large design space of deep neural network accelerators. We propose to describe this space as 3 dimensions: blocking, data flow, and resource allocation. We can decouple the resource allocation from the scheduling, which is the data flow blocking plane. We can study the impact of each dimension individually by this decoupling. And next, I'm gonna go through each dimension in details. First is the blocking dimension. Blocking is a common technique to improve locality. Naively, we fetch everything from main memory with no data reuse. For every computation, it involves 2 reads and 1 write, which is a lot of memory references and consumes a large amount of energy. However, if we block the computation by tolling and reordering the loop, we can break the large data block into many smaller ones. Such a small data block can be buffered and reused inside the global buffer. In this way, we can serve the data from cheaper memories, reducing the number of accesses to the slower and expensive memory. Actually, there are many ways to get the small blocks, given the high dimensionality of the loop blocking choices. The next dimension is data flow. Assume we have more than 1 processing elements for computation. The choice about which dimension to parallel, which data stays stationary inside the PE local register file to be reused, is called data flow. We group them based on the parallel or unrolled loops. Here are some examples. For the first one, we unroll the input channel to get a reduction tree. In this case, the partial results accumulates and flows through the reduction tree. The second example is a row stationary accelerator such as Iris. By unrolling the filter height and image height dimension, the weight flows horizontally and the outputs are accumulated vertically. The inputs are flowed diagonally. The last example basically converts a convolution operation into a matrix multiplication computation by unrolling the input feature and the output feature channel dimension. This is also called weight stationary. Note here, our data flow terminology is slightly different from the one used in the Iris paper. Our data flow only contains the choice about loop unrolls or loop parallels, but for the Iris, in the Iris data flow terminology, it contains both the loop unrolling and loop blocking choices. The last dimension is resource allocation. It is about the design choices including but not limited to how many levels in the memory hierarchy and the size of each level. Choosing the proper buffer size is important due to this trade-off. When we use larger buffer, we can cache more data, but each access to this buffer also becomes more expensive. Now we have shown all these three dimensions. We put previous designs into this space. The results are shown here. The coordinates on the data flow axis are different data flow choices. The coordinates on the resource axis are different hardware configurations. The first element is the number of PEs in the array, and the second and third elements are the register file size and the global buffer size. We can see from this figure, the previous design in the space are scattered around. There is no clear pattern, and thus it's very hard to fairly compare them and figure out the most important factor in the space. So that raises our first question: how to fairly compare various designs, how to find the most significant factors given the different design choices used by the previous designs. And our solution is to frame them as different loop transformations. This is the 3D design space we have shown earlier. And we realize the blocking dimension can be expressed by loop split and loop reorder. The data flow dimension can be expressed as loop unroll, or you can call loop parallel. For the resource allocation, you can think of it as allocate and insert buffers into the loop levels. By describing the design space by loop transformations, we can use any compilation system that's compatible with loop transformations to generate hardware design. In this work, we choose Halide to perform this task. And the reason we choose Halide is because its compact scheduling language naturally and nicely aligns with the three dimensions represented by loop transformations. Also, the decoupling between algorithm and schedule further facilitates the design space exploration. Another benefit is we can reuse Halide compilation framework. Even though it's originally designed for accelerate image processing, but internally it optimizes the linear algebra kernel. So we realize that we can also leverage to accelerate DNNs as well. Here is a brief summary of Halide schedule primitives. For blocking computation, we have split and reorder primitives. To create another level of memory, we have in primitive. To schedule compute and store granularity, we have compute at and store at. To schedule parallel computations, which basically map one operation onto multiple duplicated units, we have unroll primitive. Next, I'm going to use an example to walk through the process of generating a design using Halide schedules step by step. We start with a naive design, where we fetch everything from main memory. First, we use Halide schedule, split and reorder to block the computation so that the large input image is broken into multiple smaller tiles. Such small tiles can fit in cheaper buffer allocated in the next step. So for the next step, we use the in and computer edge to allocate local buffers. It is useful and necessary to have data communication latency and reduce access to expensive main memory. To improve the throughput, we need a way to parallel the computation. We achieve this by overloading Halide unroll primitive so that when using unrolling, we can instantiate multiple hardware units. In this case, we have 4 PEs instantiated. To generate the systolic array, we extend the Halide scheduling language by adding a new primitive systolic. It is used to create a systolic to further reduce the energy by replacing local buffer access with access to neighbor PEs. We have shown loop-based data flow taxonomy naturally aligns with Halide scheduling language. We can use Halide unroll primitive to generate different data flow microarchitectures. For example, if we unroll the input image channel dimension C, we get a reduction tree in the first example. If we unroll the filter head and image head dimension Fy and Y, we can get a row stationary microarchitecture such as the second example. If we unroll the input and output image channel dimension C and K, we got a way stationary architecture similar to the third example shown here. In such way, we map Halide scheduling primitive to the 3 dimensions. We can optimize along different access by using corresponding schedule primitives. For example, we can optimize blocking by split and reorder primitive. We can optimize data flow by unroll primitive, and we can optimize resource allocation by in and compute edge. Previous designs have focused on data flow and blocking, which explore the choices in the yellow mapping plane. Later, we are going to show that the blue optimizing plane actually has a larger variance. Although we can use Halide hardware toolchain to generate and synthesize hardware, it generally takes long cycles. To rapidly explore the large design space, we also created an analytical model to analyze and search the space. Use this model, since we already decoupled the 3 dimensions, we can optimize each dimension individually. And our model takes the layer configuration and the cost model as input to estimate energy. The energy consumption contains 2 parts, memory and computation energy, and the memory is computed by the number of access times the energy per access. If you are interested in the accuracy of our model and the validation of our model, you can find more details in our paper. Before going to the result, here is our experiment setup. We used AlexNet with batch 16 to start with. We start with a similar hardware configuration similar to Aries, such as using 16 by 16 PE array, 16-bit precision. We start with 128 kilobytes for global buffer and half kilobyte for register file, similar to the Aries hardware configuration. But we will also explore other different global buffer and register file sizes. Using our analytical model, we investigated the impact of each dimension individually. First, let's look at the data flow impact on energy efficiency. This figure, the x-axis is the data flow choices, the y-axis is the energy in picojoule. The blue dots use systolic array and the red dots use broadcast array. From this figure, we can see all the blue dots fall on the same horizontal line, roughly. Similarly, the red dots. This indicates mining data flow achieves similar and close to optimal energy efficiency, as long as we use red blocking. This is our first observation. Also compare the red and blue dots. The additional energy consumption by the broadcast array is more, and later we will show it is because the communication cost on the interconnect is only a small percentage of the overall system. Next, we look at the data flow impact on throughput. In this figure, the x-axis is the data flow choice and the y-axis is the PE resource utilization. From this figure, we can see the resource utilization difference is less than 25% among all the different data flow choices. Once enable the replication technique, which allows us to unroll multiple logical dimensions onto the same PE array physical dimension. We also investigate the impact of blocking choices. In this figure, the x-axis is the energy in picojoule, and the y-axis is the distribution, which basically is the sample size that falls into each energy bucket. We can see from this figure the energy variance is very large. Many blocking choices are inefficient, indicating choosing the right blocking choice is also very important. We already observed many data flow choices achieve similar and close to optimal energy efficiency. We further look at the energy breakdown for different PE array configurations. Here, the different bars in each group corresponds to different PE array configuration, such as 2D array, 1D array, or larger 2D array like 32 by 32, etc. This breakdown also confirms our observation that many data flows achieve similar and close to optimal energy. It is interesting to note here that the communication energy, which is the yellow bar, among the PEs is a very small portion. That explains why many data flows achieve similar energy efficiency, and broadcast the array only as a small additional energy cost. We also look at the Folicand layer here. Since there is little data reuse, the energy is dominated by the DRAM rather than communication, so data flow choice has still less impact. Another observation from this figure is we found the rectifier energy is very large among the entire system. This motivates us to look at how energy changes with changing the rectifier size and buffer size. From this figure, we can see by optimally resizing the rectifier size and buffer size, the energy efficiency can be dramatically improved, especially using smaller rectifier size. Compare the energy breakdown between using a large rectifier, such as a half kilobyte, versus smaller rectifier, such as 64 bytes. The overall system energy breakdown. The overall system energy consumption greatly reduced as we significantly reduced the rectifier energy. Even with a 64-byte rectifier, we can still capture 98% memory references for convolution layer, since the convolution layer have a large number of data reuse. Since we are able to improve energy by optimizing the memory sizes in the memory hierarchy, we further investigate whether changing the memory hierarchy can improve the energy efficiency further, for example, using a two-level rectifier. And in this figure, from this result, we can see by optimally sizing the memory hierarchy with two-level rectifier, we can further improve the system energy efficiency by another 25%. Using our analytical model, we create an auto-optimizer which jointly exhaustive search the best memory hierarchy with the best blocking for the entire networks. Using observation we obtained, where many data flows achieve similar and close to optimal energy efficiency, we fix the data flow choice to reduce the search space. For the results, all the layers use the same architecture with optimal blocking here. From this figure, we can see by optimally sizing the memory hierarchy, we can achieve up to 4.2x, 1.6x, and 1.8x for CNN, STM, MLP respectively. Let me briefly summarize our work. In this work, we found the design space can be viewed as three dimensions: blocking, data flow, and resource allocation. And all these three dimensions can be viewed as loop transformations. By viewing them in such a way, we can use Halide to generate the designs in the space. Using the analytical model validated against the design generated by the Halide to hardware framework, we found many different data flows can achieve similar and close to optimal energy efficiency. While on the other hand, optimizing memory hierarchy has a larger impact on the overall energy efficiency. Here I want to thank Xuan, Jonathan, Andrew, Steven, Keyi for all the helpful discussion. Also, I want to thank DARPA, Stanford AHA, Stanford System X, Stanford Platform Lab, CRISP for supporting this project. And if you are interested in using our analytical model, you can find our open source code repo in this link. Thanks for your attention.